Today I'll be delivering a presentation for my deep learning course project. So we use momentum detection on a DNN setup. Before we dive into details, I'll provide you with the overview. First, we go through the motivation of the project, and then we discuss the dataset choice and the DNN choice. And then we go through the loss function design and the training process. And finally, we reach the evaluation part. And for the motivation of this project, you can see that on the left side, there's an image of sad news when a self-driving car crashes into a delivery robot, which has proved that the collision of real-life robots often occur, and auto-driving engineers need to move their attention from the perception of movement into the prediction of movement, which in case is regarded by some researchers as the hardest auto-driving task. So this is more beyond auto-driving task because when you try to deploy home robots and public service robots into real world, you must make sure that it won't collide with anything or anyone, or it doesn't do any damage to the physical world or to any human being. So what we try to do is try to bridge the gap between the perception of movement and the prediction of movement. The idea is that we try to map out in which part or which objects is highly mobile, and which means it can potentially move in the future or can move fast or things like that with faster moving velocity. And after the model can get the understanding of these knowledges, and they can perform better on the prediction of movements because they can know where to focus their attention on. So the models will perform better. So for the dataset we choose a real life dataset, Coco stuff, and it includes 180,000 photos with annotations on the object type. And it is good for real world understanding because it is mostly outdoors and indoors photos taken from various angles. And we redefine the tags into 4 levels of momentum, which from highly mobile to not movable at all. And then these will be shown in the training process as well. So for the model we are using, it is the Deep Lab series because it has the SPP scheme that it can do the semantic segmentation tasks better than any other kinds of model. So for the structure of the model, we use a backbone of DeepLab v3 ResNet 50 as our backbone to convolute RGB image of 512 by 512 into a 64 by 64 by 2048 feature map. And then we input this feature map into the SPP module to extract the features. And then we use a multi-scale classifier to obtain a 64 by 64 by 4 mask result, and we scale up using the bilinear interpolation for the mask to be with the original size. So we rewrite the SPP module by deleting one of the SPP layer of asteroid rate of 24, and then we try to remove the image pooling layer of the SPP head. And also the bilinear interpolation stride is 8 instead of 16, and these will be reducing the training and inference cost by 20% than the original network. So for the loss function design, we use the weight cross entropy loss, and to emphasize the high mobility things, which we define the weight WC as the pixel level frequency of each kind of each kinds of the tags objects reversed. So which means we put more attention on the objects with a certain tag that occupies less pixels. So we pass down this weight also to the IOU calculation, which we use a differentiable soft IOU that can achieve better convergence in segmentation over smaller objects. And finally, we combine the two parts of the loss function with another two parameters to scale up the training process, which we want to achieve a balance between segmentation and the understanding part. For the actual training, we first create the projection LUT, and we redefine the labels into new labels of 0, 1, 2, and 3. And then we use large language models to cross-check the annotation. And for the training part, we've tried to validate the pipeline with 10 epochs as first, and everything seems normal, and the segmentation results improved significantly after 10 epochs. And then we apply the real training with 50 epochs on 9.6 thousand images, and the result converges after 45 epochs over the loss on the validation set and the IOU score. And you can clearly see the segmentation result is better after 50 epochs, and it achieved a very brilliant level when you can see the people and skateboard and mapped out in this image. So for the validation part, we randomly choose images from the test set, and we perform the inference on them. And you can see that the model can predict the objects with high mobility with a very fast inference time of 58.21 FPS, average from 1,000 samples. So in the end, I want to thank Professor Hongsheng Li for supervising this project and his PhDs. And that will be all of my presentation. Thank you.